Okay, hello everyone. Today we will learn about functions of random variable, which is chapter 6 of the textbook. Okay, let's go. Chapter 6.1 is a little bit of introduction that is about why the functions of random variables is an important concept in statistics. So the objective of statistics is to make inferences about a population based on information contained in a sample taken from that population. So to make that inference, well, what we usually do is taking n random observations and calculate statistic with that. Or quantities used to estimate population parameters or to make decisions about the population are functions of the n random observations that appear in a sample. So many useful statistics. For example, sample mean, which is mean of all the sample that we have. This is an example of functions of the n random observations, which is functions of random variables. So this chapter is important in that most of the statistic is calculated from n random observations. So here's a bit of introduction. And in most situations, populations are large in comparison to the sample size. So consequently, the random variables obtained through a random sample, we can assume that they are independent of one another. So we are assuming that joint probability function for random variables y1 to yn, they are independent samples from the population. And for discrete case, we usually assume this situation, or since all y1 to yn are independent random variables, the joint density, joint probability function is p of y1 to yn can be derived as py1 times py2 times pyn. And also for continuous case, the density function fy1 to yn can be described like this: fy1 times fy2 times dot 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 fyn. Okay. And chapter 6.2 is about finding the probability distribution of a function of random variables. Consider random variables y1 to yn and a function u of y1 to yn. So u is function of random variables y1 to yn, and there are three methods for finding u, which is function of random variables. So here u is function of random variables, and we here are three methods for finding distribution of function of random variables. We are going to learn chapter 6.3, the method of distribution functions, and in chapter 6.4, we will learn about the method of transformations, and in chapter 6.5, we will learn the method of moment generating functions. Okay, let's start one by one. So in chapter 6.3, we will going to learn about the method of distribution functions. And if y has a probability density function fy, and if u is some function of y, then we can find fu. Fu, this is distribution function. Pu is less than or equal to small u directly by integrating fy over the region for which u is less than or equal to u. I will go over simple examples to see what this means. And okay, the probability in this density function for u is found by differentiating fu u. Okay, let's see the example to check what it means. Okay, let's go about example 6.1. A process for refining sugar yields up to 1 ton of pure sugar per day, but the actual amount produced, Y, is a random variable because of machine breakdowns and other slowdowns. Um, so we can produce sugar up to 1 ton, but because of the machine breakdown or other slowdowns, uh, we can earn less than 1 ton, and it's random variable y. Suppose that y has density function given by this. So from 0 ton to 1 ton, and we have density function 2y, and the company is paid at the rate of $300 per ton for the refined sugar, but it also has a fixed overhead cost of $100 per day. Um, Thus, the daily profit in hundreds of dollars is U is 3y minus 1, and find the probability density function for U. Okay, so probability of U is less than or equal to U. We By the method of distribution function, we calculate this one directly to find f u of u, and then we differentiate this f u of u to find um, uh, density function for u. Okay, so what is it? The probability of u is less than small u. By definition, u is 3y minus 1. Okay, and from here, this is same as probability of um, uh, we can move minus 1 to this side and move this 3, which is 2 over 3. Okay, and oh, sorry, this part is u, so u plus 1. U plus 1 over 3. And okay, and how can we calculate this one? From the density function, we can integrate y from 0 to u plus 1 over 3. And this part is 2y and dy. And this is integration of if we integrate 2y, it is y square, and from 0 to u plus 1 over 3, and this is 9 u plus 1 square. Okay, so this is what we got for fu to u, and here, since we have y is from 0 to 1, 3y minus 1 is actually 3y is 3 and minus 1, minus 1 to 2, and this is u. So when u is larger than minus 1 to 2, then the distribution function is this one. So fu of u can be written as this. 0 if u is less than minus 1, less than or equal to minus 1, and u plus 1 squared over 9 when u is greater than minus 1 or less than or equal to 2, and 1 if u is larger than 2. Okay, so this is distribution function for fu of u. And to calculate density function, you differentiate the distribution function. Then it is 2 times 2 over 9 u plus 1. And for u is minus 1 to 2. And as you know, the differentiating constant 0 or 1, that's 0. So fu of u are defined like this, and 0 otherwise. Okay, so here's what you get. Okay. Okay, let's move on to example 6.2. In example 5.4, we considered the random variables y1 and y2. And here y1 is the proportional amount of gasoline stocked at the beginning of a week, and y2 is the proportional amount of gasoline sold during the week. The joint density function of y1 and y2 is given by this formula. And find the probability density function for u, which is y1 minus y2, and this is the proportional amount of gasoline remaining at the end of the week. And so this u is function of random variables y1 and y2, and so we were going to use the method of distribution function to calculate density function of u, and use the density function of u to find expected value of u. Okay, so let's find the density function of u first by using the method of distribution function. And so what is method of distribution function? We want to firstly calculate fu of small u, which is probability of u is less than or equal to small u, and we will differentiate it with respect to u to calculate the density function for u. Okay, so what's this? This is probability of y1 minus y2 is less than or equal to u. And how can we calculate this probability? To calculate this probability, and actually we know the joint distribution of y1 and y2. So the joint distribution of y1 and y2 is this one, and we can integrate the density function over this region. So we have a density function of fy1 and y2, and to calculate their probability, we calculate that probability by integrating the density function over this region. So let's write what is the region, what is this region. So let's draw the graph. So here this part can draw the region for this bigger rectangle. So y2 is greater than, or y2 is less than or equal to y1, and both y2 and y1 are greater than or equal to 0 and less than or equal to 1. So it describes the bigger rectangle, and if you integrate this density function over this bigger rectangle, it is sum up to 1. And what we want to calculate is we want to calculate probability of y1 minus y2 is less than or equal to u. So we want to find the region, what is y1 minus y2 is less than or equal to u. What would be the region for this? And here y2 y1 minus u is less than or equal to y2. So this is the region. Y2 is equal to y1 minus u, which is this line. and this line, and the region here is this black one. So this area, if you integrate the density function here on this shaded rectangle, then you can find the probability of this thing. Okay, we want to integrate the density function over this region, and this is actually if you integrate it, this is double integration, dy2, dy1, and for y1, we are integrating from 0 to 1. So, however, when we are integrating it from 0 to 1, we also we are integrating at each point. You will going to integrate from y2 from here to here, and the line would be different. So when y1 is from 0 to u, when y1 is from 0 to u, then the integration of y2 is from 0 to here, and this is y1 equals y2. So y1, this part is y1, and 3y1 and plus double integration. So dy1 is from 0 to u, and again it is from u to 1, dy2 dy1. When y1 is u to 1, then what is y2? Y2 is defined from here to here. So this one is from this formula. This is y1 minus u. So y1 minus u to y1. So 3y1. Okay, so if you want to find the probability density over this region, you should divide this region by two parts, and you can calculate it by integrating these two, um, or the density is sum up to 1. So you can also calculate uh, 1 minus integrating the density over this small region, which is explained in the textbook. So whatever you are familiar with, you can go on with that. So if actually this is same as 1 minus the dy1 dy2 dy2 dy1, and for this one, dy1 is from u to 1, dy1 is from u to 1, and then y2 is from 0 to y1 minus u, 0 to y1 minus u, and 3y1. This one looks more easier to calculate, so I will do it this one, and you can also calculate this one as well, and you can check these two are actually the same. Okay, I will explain it from the next slide. From the previous slide, we are calculating f of u of small u, which is probability of u is less than or equal to small u, and we can calculate directly this one. However, it would be easier to calculate this one, which is 1 minus p of u is larger than or equal to small u, which is, so this one is integrating this one minus integrating this one, and integrating this one is 1, minus this one is integrating density function over this region. Okay, so let's calculate this one. This is 1 minus integration from u to 1, and this is 3 y1 y2, and y2 is 0, y2 is y1 minus u, and dy1. And this is actually um, integration u1. Y2 is 3, y1 y1 minus u, and dy1, and this is 3y1 squared minus 3y1 u, and this is 1 minus y1 third minus 2 over 3 over 2 u y1 square, and integration is from u to 1. Okay, so this is 1 minus, and if we put 1 minus 3 over 2 u, and minus u third minus 3 over 2 u third, and this is 1 over minus 1 over 2 u third, and actually plus third minus 3 over 2 u plus 1 plus 1, or minus this one. 1 minus this whole thing, and it's sorry for the bad space managing, and 1 can be cancelled, and it's 3 over 2 u minus 1 over 2 u third, and u is from 0 to 1, 0 to 1. Okay, so this is what we get, and you can calculate f of u by differentiating this one. So it is 3 over 2 minus 3 over 2 u squared, and for u is this one, and 0 otherwise. 0 otherwise. Okay, so here's density function of u, and to calculate expected value of u, you can use this density function, integration u of density function of u du, and from 0 to 1, and you can calculate it by yourself, so finish it by yourself. Okay, let's go to example 6.3. Let y1 and y2 denote a random sample of size n equals 2 from the uniform distribution on the interval 0 and 1. Okay, find the probability density function for u is y1 plus y2. And here, what it means is that y1 is uniform sample from 0, 1, and y2 is another independent sample from 0, 1. And so f1 y1 is 1 or 0, y1 is 0 to 1, and 0 otherwise, and y2 is the same. And since those y1 and y2 are independent samples, the joint density of y1 y2 is 1, and both y1 and y2 are from 0 to 1 and otherwise 0. So it is defined on this 0, 1 region, here y1 axis, y2 axis, and uniformly distributed on this rectangular region. That's the joint density. And what we want to find is the probability density function for u, which is y1 plus y2. And to calculate the density function for u, we can use the method of distribution function. So we want to calculate fu of small u, which is probability of y1 plus y2, because u is y1 plus y2, and it is less than or equal to small u. And to calculate this probability, we know the joint density function of y1 and y2. We already know the joint density function, so we can calculate this probability by integrating the density function, by integrating the joint density function of y1 and y2 over this region. So y1 plus y2 is less than or equal to u. What's the region of this? Actually, here there are two different cases. Let's look at what this area looks like. Y1 plus y2 is less than or equal to u. And so what it means is y2 is less than or equal to u minus y1. So so here's u, and the y2 is less than or equal to u minus y1. So this is this triangular region, and the density is defined on this rectangular region. So intersection of those two area, the probability is defined on this intersecting area. And however, this intersecting area is different depend on value u. So you should calculate this depending on value u. And actually, if u is less than 0, there's no intersecting area. So if u is less than 0, and the probability is 0, and if u is greater than equal to 0 and less than or equal to 1, you calculate you integrate the probability over this triangular region to get the probability here. And if u is greater than or equal to 1 to 2, which is this case, so you integrate this region to calculate the probability for here. And if u is greater than or equal to 2, then the intersecting area, when u is greater than 2, intersecting area is everything, and integration over this rectangular area is 1, so this is 1. And so what we need to calculate is this box 1 and box 2. And to calculate box 1, we calculate the probability over this triangular region, this case. And so for this case, fu of u, this is integration of dy2 dy1, and y1 is from 0 to u. No. um, oh yeah, it's so uh, so this this axis is y1, and y1, when y1 is 0, y2 is u. So um, this is from 0 to u, and y1 is 0 to u, and for y2 it is from 0 to 0 to what is this point? Um, mm, u minus y, u minus y1, u minus y1. Okay, and density is 1. So to calculate the probability or that defined on this region, you can integrate this thing. Okay, and what about this case? This case, you can calculate f of u. This is integration of and actually to calculate this one, it's easier to calculate 1 minus probability of y1 plus y2 is greater than or equal to u, which is the, um, this area A, probability defined on area A. This is probability defined on area A. This is simpler, so which is 1 minus double integration dy2 dy1, and y1 is from here, from this point to here, and this point is y2 equals 1, and this line is y1 plus y2 equals u, so y2 equals 1, and then y1 is u minus 1, u minus 1, so u minus 1, u minus 1 to 1, so y1 is defined from u minus 1 to 1, and uh, and y2 y2 is defined from here. What's this? U minus y1, u minus y1 to 1, and here 1. Okay, so you can calculate this probability by yourself. Do it by yourself, and you can calculate the density function by differentiating this with respect to small u, and that's the probability density function for u. Okay. Do it by yourself, and actually in the textbook it is also explained, so follow that example, and if you have any questions you can email me. So far, we have learned about the method of distribution function, and here's summary of the distribution function method. Let u be a function of the random variables y1 to yn, and the first thing is find the region u equals smaller u in the y1 to yn space, and find the region u is less than equal to small u, and the third, find fu of u by integrating the joint density function of y1 to yn over the region u is less than or equal to small u. And number 4, to find the density function of fu of u, differentiate large fu of u with respect to small u to calculate the density function for u. And then that's the summary for the distribution function method. Okay. to illustrate the summary, we will consider the case u is y squared. And to calculate fu of small u, which is probability of y squared is less than or equal to small u, and actually this one, we can calculate this with minus square root of u is greater than y, and like this. So this region is like this one, and since we know the density function for y, we can calculate this with density function of y. So integration is from minus square root of u to square root of u, and we know the density function of y, uh, fy, and dy, and if we integrate it, uh, and we know that f of y, this is from minus infinity to y, f y dy. So this is actually um, mm, f of this is actually integration from minus infinity to square root of u f of y dy minus minus infinity to minus square root of u f of y dy. So this is f of square root of u, and this is minus f of minus square root of u. Okay. Um, and and uh, and apparently u is greater than or equal to 0, because if u is less than or equal to 0, this area, there's no such area. Okay, so it's like this, and um, to calculate f of u, you differentiate this with respect to u. So f of y is f of square root of u, and if you differentiate 1 over 2u, it is 1 over 2u minus 1 over 2, and minus, and if you differentiate this side, it is plus f of minus square root of u, and also you differentiate this side, which is 1 over 2 u minus 1 over 2, and actually there is minus, and this part cancelled, and this part become plus. Okay, and here again u is greater than 0, so and 0 otherwise. Okay. um, yeah. Let's move on to example 6.4. Let y have probability density function given by this one, and find the density function for u is y square. And we proved the density function for this case. So f u of small u, previously we calculated it as 1 over 2 u minus 1 over 2 f of fy of square root of u plus 1 over 2 u minus 1 over 2 f y minus square root of u for u is greater than or equal to 0, and for other regions 0. Okay, so you calculate this by yourself, and to find the density function for you, but do it by yourself, and refer to the textbook for the solution. Okay. Okay, let's move on to example 6.5. Let u be a uniform random variable on the interval 0, 1, and find the transformation g of u such that g of u possesses exponential distribution with mean beta. So here u, f of u, uh, if it is follows uniform distribution, it is 1, 0, and u is defined on 0, 1 interval, and 0 otherwise. And if y is g of u, and then f of y is equal to 1 over beta, expected value of minus 1 over y over beta. For y is greater than 0, and 0 otherwise. So this is density function for exponential distribution, and if you calculate distribution function f of u, which is probability of u is less than equal to small u, and this is if u is less than 0, if u is less than 0, then this region is not included, and density function is 0 otherwise, so it is 0. And when u is 0 to 1, if you integrate this density function on this 0 on this region, you will easily find this is u. And when u is greater than or equal to 1, then this whole interval is included, and you can calculate this distribution function have value 1. Okay, this is distribution function for u. And what would be the distribution function for exponential distribution, f of y? And this is probability of y is less than or equal to small y, and this is if y is less than 0, it is the density is 0 for this case, so integration is again 0. And if y is greater than or equal to 0, you integrate the density function, you integrate this density function from minus infinity to actually it is 0 to y, 1 minus beta e to the minus y over beta dy. If you integrate it, it is 1 minus e to the minus y over beta. You can easily calculate it from here. And what's next? We want to find y is g of u that possesses the exponential distribution function. And to do that, actually, let's equate these two. What will be happen? So if we set u equals 1 minus e to the minus y over beta, what's happening? Here, u is defined on 0 to 1, and y is defined on this region. And here, when y equals 0, when y equals 0, u is, when y equals 0, e to the 0 is 1, 1 minus 1 is 0, so u equals 0, and when y goes to infinity, e to the negative infinity goes to 0. So 1 minus 0 is 0. 1 minus 0 is 1. So u goes to 1. So this one is well defined for this situation and that situation. So what we want to do is let try y equals g of u, and try let's take inverse form of this, and then let g of y of like this form. So from here, 1 minus u equals e to the minus y over beta, and ln 1 minus u is minus y over beta, and so y is minus beta times ln 1 minus u. So let's take this as g of u. And then what's happening? So f of y is actually calculating probability of y is less than or equal to small y, and if we use this is probability of minus beta and 1 minus u is less than equal to small y. And this is actually the probability of y over beta negative, so the sign change it, and 1 minus u, and this is 1 minus u is greater than e to the minus y over beta, and u is less than or equal to 1 minus e to the minus y over beta. Okay, so we want to calculate this thing, and for here, if y is less than 0, if y is less than 0, and actually this part is not defined. It will be never go below 0. So this part actually always larger than 1. So the probability for y is less than 0 is 0, and for y is greater than 0. For this part, uh, use distribution function for u, and calculate it for 1 minus e to the minus y over b. That is actually 1 minus e to the minus y over beta, which is actually the same as this one. So we prove that our g of y is minus beta times ln 1 minus u. Okay. Here are homework for chapter 6.3. Okay, let's learn about the chapter 6.4, the method of transformations. And suppose that h of y is an increasing function of y, and that u is hy, where y has density function of fy. So we know this, and we want to find the density function for u. Okay, and by applying the method of distribution that we learned in chapter 6.3, probability of u is less than equal to small u is probability of h of y is less than or equal to u, and from here, if we get this one, this part not change it, because this is increasing function, and this is actually probability of y is less than equal to h inverse small u, and this is actually fy of h inverse u. And from here, here, then differentiate it with respect to u. So to get the density function for u, which is this thing, and to simplify the notation, to calculate fu of small u, you can derive this formula. And actually, this formula is derived from the method of distribution. But you can simply use this method. This is the method of transformations, and it would be easier to calculate uh, um, uh, rather than using all the definitions of the method of distribution. You just memorize this and apply this for the simple cases. Okay, let's try to solve example questions. Here, the example 6.6. In example 6.1, we worked with the random variable y, amount of sugar produced, with the density function given by here. And we were interested in a new random variable given by u equals 3y minus 1, and find the probability density function for u by transformation method. And what I usually use is that to calculate f of u, small u, actually I write like this way. Fu du is f y dy, and then fu u is fy dy du. And we have u equals 3y minus 1, and u plus 1 over 3 equals y. So it is f of u plus 1 over 3, and this is y. So dy du is differentiated with respect to u, which is 1 over 3. So 1 over 3. And so this is fy, 2y, it is 2 over 3 u plus 1, and uh, and 0 to 3 over u plus 1 is less than or equal to 1. And this is 0 to 3, u is minus 1 to 2, 0 otherwise. Um, uh, uh, you can memorize the previous formula that I defined, just like textbook, but I find it is useful to apply the formula. So when I am solving the method of transformation, I usually write the formula this way: fu du is fy y dy, and then convert it to fu u is fy times absolute value of dy du, and um, solve like this. I find this way is easier than the textbook solution. So try to look at the solution for in the textbook for example 6.6, and if this looks easier, you can solve it this way, or you can use the method in the textbook. And actually, they are the same. Um, I just write this way since I think this is a bit simpler than that. Okay. And if y is a decreasing function of y, then the probability of u is less than equal to u, and this uh, the the area, the part is shifted, and so fu of u is 1 minus this thing, and from here fu of u differentiate this part is negative of this thing, and simply by simplifying it, Um, actually, um, actually, by simplifying it, you can find that this can be written as this way: whether h of y be increasing or decreasing, if you use this abstract notation, then you can apply this one for both when hy is increasing or either decreasing case, and uh, and just like I mentioned, I usually use this way: f of u small u du is equal to f of y small y dy, and when we are calculating f of u small u is equal to f of y small y dy du and absolute value, and I usually write this way, um, just for the memorizing this formula better. And actually, you can use this directly. Okay. Let's move on to example 6.7. Let y have the probability density function given by this, and find the density function of u equal to this thing. Okay, so here let's find fu, the density function of u, du equals fy y dy and du dy. Okay, so um, u equals minus 4 y plus 3, and from here u minus 3 equals to minus 4y, and y equals minus 4 u minus 3. Okay, this one, and so f of u u is f of y, and y is this one, so minus u minus 3 over 4 dy du, and dy du absolute value is absolute value of minus 1 over 4. It is 1 over 4, so times 1 over 4, and this is 2 times negative 2 times 4 u minus 3 times 1 over 4, and uh, and minus 4y is minus 4 to 0, and minus 4y plus 3 is minus 1 to 3, and this is u. So u is from minus 1 to 3. Okay, and this part is 3 minus u over 8. -1 to 3 and 0 otherwise. Okay. For example 6.8 and 6.9, I will come back to these questions after we learned chapter 6.6. Then it would be easier to solve these example questions after we learned chapter 6.6. So I will back to these example questions again after we learned chapter 6.6. Here's summary of the transformation method. Let U is h of y, and and uh, and to find the distribution function for U, actually you can find this one. And simpler way to memorize this equation is that what I use is Fu U equals Fy y and dy du. Actually, this equation is what I usually write, and actually these are same thing, but I find it easier to memorize this way, so that's what I use. Okay, and here are homework for chapter 6.4. Okay, so far we have learned the method of distribution function and the method of transformation. In the next lecture, we were going to learn the method of moment generating function, which is the last one to calculate the density function for function of random variables. Okay, see you in the next class.